Yes. So I hope yesterday's lecture was more or less you understood what we are talking about. So in this new device, is also semiconductor device, we are having two junctions instead of one junction that we saw in diodes. So here we have two junctions, and that gives rise to the different analysis or different characteristics. So we had seen how it behaves, the physics behind it. There are basically two different loops, two different current loops which are set up when the transistor is biased. So one is in the base and another is in the collector. So let me share the screen and we will move a bit ahead now. So yesterday we talked about this common emitter configuration, and in the common emitter configuration we analyzed the circuit using our very well known KVL, KCL, these equations. So these are very fundamental laws. So every electronic or electrical circuit will always obey KVL, KCL. So that we utilized, and along with it certain special laws, or what we should say, that certain special features of the transistor was utilized. What these special features are? These are like this current gain, which is a very unique parameter of the BJT, and this is decided by the manufacturer. So this beta DC is known to us and we utilize this fact also. So this is a fact about the particular device. Okay. Yeah.
सर क्लास रिकॉर्ड नहीं कर रहे हो क्या सर आप?
Yeah, I am recording.
सर नहीं सर, चालू नहीं हुआ है अभी तक.
अरे I record in a separate software. I don't record in the Teams.
Okay, thank you.
So you should have noticed this from the first class only. So this is my recording software. You can see it is recording.
Sir, actually I thought इधर भी start recording की जगह stop दिखाता है, तो sorry sir, disturb करने के लिए.
ठीक है, चलो. So you see that what we are utilizing, similar to the diode, we are utilizing the characteristics of the transistor. Some specific properties of the transistor are there that we are utilizing along with the KVL and KCL. Okay, which are universal truths. KVL and KCL are universal truths for any circuit, and in a particular circuit some specific truths are also there. Specific truths of a circuit are the truths or the facts related to a particular device which is present in the circuit. So we have to work with these two laws. One is the universal law and another is the particular law. One is the universal truth, another is the specific truth. Okay, so we have to work with these two things in any problem that we are working out, and this idea is also a very universal idea. So this is not restricted to analysis of electrical circuits. This you can apply to any other domain of your study as well as in your life. You will see that there are some universal truths governing the particular thing, and some specific truths. So within the universal, in the domain of the universal truth, some specific truths are acting. So we have to analyze both these taken together. So this happens in everywhere. This happens everywhere, in any subject, in any domain of knowledge, in any field of study, even in your personal life, in social life, everywhere. So this is a very universal thing that you can keep in your mind. So whenever you look at different phenomenon happening in nature, phenomenon happening in your life, you might be able to categorize what is the universal truth and what is the specific truth, and that helps a lot in our understanding. Okay, so we move ahead and we try to understand. So this we understood the equations, and now we try to understand the characteristics of the diode, the characteristic curves. So there are two characteristic curves. One is the input characteristics or the base curve, another is the output characteristic or the collector curve. We are mostly concerned about the collector curve because the base curve is nothing but a diode characteristics. Because base curve, you see what are the input and output in the base curve. VBE, this is the junction voltage, VBE of the base emitter diode, VBE. IB is the current through that diode in the forward biased condition. This base emitter diode is in forward bias condition. So this is simply a diode characteristics. We all know this. So this is simply diode characteristics. Not very interesting at this stage. When we are talking about, when we are reading diodes, it was very interesting, something new. But now it is very standard to us. It is not interesting. What is interesting now is this new characteristics that we see when we plot VC versus IC. Now remember, what is the output characteristics means? We have to deal with the output current, and IC is the output current because it is what is coming out of the transistor and going into a subsequent circuit where we have placed RC. In place of RC, it could be some different circuit altogether, some load circuit. Okay, here it is just a simple resistive load. So that RC is there, so IC is flowing in that load. So IC is the output current, and that output current versus the output voltage across the transistor. Since we are concerned about simply the device, we are concerned about the voltage across the device only, no other voltage in the circuit, only across the device. So VCE versus IC plot we have to make, and when we are making this plot, we see that the curve takes a shape like this. So it rises a bit, follow one particular curve, suppose a 30 microampere curve. What is this? I will tell you. Suppose this 30 microampere curve we are following. So it rises when we increase this VCE. How we increase VCE? We can change the VCC, the bias voltage across the collector, that we can change, and that will change VCE. Okay, that will change VCE. So the VCE is changing, and we see that IC is also increasing a bit. Then it becomes constant, remains constant for a long period of time, and after a while it suddenly takes a peak up and just goes to a very high value of current, and the voltage does not change very appreciably. So this is the nature of the curve that we are seeing, and now we have to understand why we are seeing this nature of the curve. The first thing is, what are these 0, 10 microampere, 20 micro, what are these values? These values are different base currents, different base currents. So as you know, as you remember this circuit, so let us see this circuit once more. You can see that this current is quite independent of this circuit. So this IB current is simply set up by this VBB voltage. So whatever you set this voltage, this VBE drop is constant always. So this IB current simply depends on this voltage. So you increase this voltage, IB will keep on increasing. For a particular IB, you can now change this VCC. To set up a particular IB, now you change this VCC. What will happen? Your VCE and IC you will plot, and you will get a curve like this. Now you increase your IB, you will get another curve. You decrease your IB, you will get another curve. But all these curves will look exactly similar. They have the similar characteristics. So these are the IC VCE curve for different values of IB, 10, 20, 30, 40, like this. So if someone asks you to plot the collector curve or the output characteristics of a BJT for suppose 25 microampere of base current, then what you will do, you will have to bias the circuit in such a way that you get 25 microampere in this particular circuit. So you choose your VB is known always fixed, you choose your VBB and RB in such a way that you get 25 microampere here. Once that is set, then you keep on changing VCC. You start from 0. This is always in the positive region, because the direction cannot change, because we have to reverse bias the collector base junction. So this is the only direction of voltage that you are supposed to apply. So you start from 0 and keep on increasing the voltage, and you note down what is IC, and then you plot it. You will get the collector curve. Now when we got this curve, then we can see there are four distinct regions available in the curve. These 4 distinct regions we have to understand. First, let us understand the active region, which is a very easy one to understand. The active region is where we would like to operate the common emitter configuration. Suppose then this current gain, the idea of current gain is applicable in the active region only. You can see, because you can see that the base current and the IC, the collector current, is directly related by a current gain. So if it is 10 microampere base current, it is 1 milliampere IC. If it is 20 microampere IB, 2 milliampere IC. So the current gain is always fixed in the active region. We appreciate this fact. So this is the idea of the active region. The active region is that region where you have a constant amplification of the current. Constant amplification of the current. That is the active region. However, we are not always in the active region. So last day we solved this circuit with the idea of current gain. However, the pre-assumption here was that we are working in the active region, but this may not be always so. So this idea of current gain and applying this formula IC equals to beta IB, this is only possible when we know that we are in the active region. However, if we are not sure whether we are in the active region, then we have to first understand whether we are in the active region or not. So this is the idea of active region. However, when we actually start increasing VCE, then first we see this rising curve. First the IC rises a bit and then becomes constant. So during the constant IC region, that is where the active region is, and that is where the current gain can be applied. The formula IC equals to beta IB can be applied. But before this region there is a rising region of the current. What is this region? You see VCE is what it is doing? VCE is not the reverse bias potential across the collector base junction. VCE is the total potential across collector and emitter. However, VCE is causing a reverse bias in the collector base junction. So when you have VCE starting from 0, then you are initiating the reverse bias condition in the collector base junction. So when the reverse bias condition is getting initiated, what happens? There is a saturation region, there is a saturation current in the reverse bias region for some time. So that saturation has to happen. So this is the saturation region. After a certain amount of voltage is passed, then the constant current region comes in, which is the active region. So this phenomenon happens, what we have explained earlier. So this active region phenomenon takes over now. Now you keep on increasing VCE. What is happening when you keep on increasing VCE? The reverse bias across collector base. The reverse bias across collector base is increasing. When it reaches a certain level, of course you know, breakdown will take place. So when the reverse bias potential, reverse bias across the CB junction is more than the breakdown voltage of the CB junction, then reverse bias will take, then breakdown will take place, and this will destroy the transistor. We will not be able to bring back the transistor to its normal modes of operation. So we have to know what is the breakdown voltage here for each of the curve. You see that more or less it is around 40 volt. Okay, as you keep on increasing the base current, this breakdown voltage also decreases. This breakdown voltage also decreases. There is another region which is the cutoff region. So you see that when we have a IB of 0 volt, 0 amperes, when the IB is 0, then also there is some IC. IC is not 0. This we learned yesterday. IC is basically like this. This is true always. So when IB is 0, then also there is some IC because of the this reverse saturation current of the collector based diode. So this is coming here. This level is, you can see here. However, this is quite small, and you cannot take the transistor to any level of IB which is less than this, because the B junction is forward biased, so the current cannot be negative in here. So we are not going to a negative current, and the transistor will never operate in a region which is lower than this particular curve, this 0 IB curve. We cannot have the transistor operate in this particular region. So it is a cutoff region. So if for some reason you come here, it means the transistor is not in the circuit. So the transistor is open circuit. In that case, the transistor is open circuit. So you see these two figures. One is when the transistor is shorted and one is when the transistor is open. What does this mean? From this collector curve, mental short, the IC being short, means VCE is 0. 0 means this line, this vertical line. Why they are saying mental short? This condition never appears actually, because in reality the current is rising and it has a slope associated with it. So when VC is 0, the IC is also 0. But we may consider, since this is very small amount of voltage, we may consider that this region is basically a straight line in this axis. This is an approximation. This is an approximation we can do for some simplistic analysis to just understand what would be the current when we are in saturation. To understand that, we apply this idea of mental shorting. So this idea is applied when we are trying to understand saturation. operation in saturation region. Previously we are talking about operation in active region. So we took the understanding of the current gain. However, when we know that the transistor is in saturation, we cannot apply the idea of current gain. Then what idea we apply? We apply this simplification of mentally shorting the transistor, because during saturation Vc is so small that we can almost take it as 0. So when we take it as 0, then what is the current in this circuit IC, that we need to calculate, and we can say the saturation current is that much. That's all. It is not exactly that, but it is nearly that. So IC during saturation is nearly this value VCC divided by this value, which is RC. That much only, because this is 0 volt. So it is simply 15 by 3, which is 5 milliampere in this case. So saturation, in the saturation region your current will be near about 5 milliampere. Okay, so that is what we analyze. How we analyze the saturation current is with this idea of mental shorting. What is this idea? This idea is mental opening. This is when we are working in the cutoff region. When we mentally open it, cutoff means there is no current, it is open, no current in the load side, IC is 0. So IC, as you can see, is not basically 0, it is very small quantity we can have IC, but for analysis purpose we approximate it to be totally 0, and then obviously IC is 0. So what we need to ascertain is the voltage across this transistor. What is the voltage across this transistor? What is VCE in this condition? So this is the cutoff condition which we are trying to analyze using this mentally open circuit, and in this case you will find out VCE in the situation that IC is 0 and VC is simply VCC.
15.
Obviously this is approximately, because there is some IC, but that drop is inappreciable. We must write this along with it. So this is the operating point in the cutoff region, this is the operating point in the saturation region. So this is the operating point in the cutoff region, this is the operating point in the saturation region. So you see that we have found out the cutoff point. VCE equals to VCC for this particular circuit. VCC and IC is 0. We have found out the saturation point, 5 milliampere, and VCE is 0. This is the saturation point, right? Though you should keep in mind these are approximation, but quite valid approximations. And these 2 points are also part of the load line that we will create using the KVL equation. This is the output side KVL equation. You can see my cursor. So this is the output side KVL equation. So when you try to plot this KVL equation, then those 2 points, the saturation and the cutoff points, approximated saturation and the cutoff points, they are part of that load line, and any other value of voltage and any other value of VCE and IC which appears in the circuit will be on this load line. So now we have a load line coming into picture. And we are not operating in the breakdown region, so we don't need to worry about it. But other possible regions of operation can be cutoff, saturation, as well as the active region. So now in the active region we are setting up some current IB. So if you know the amount of current, suppose it is this current which might be 20 microampere. So I am supposing the gain of 100. So this is 20 microampere. So in 20 microampere IB, if you are asked to find out the operating point, it would be this particular point. And from here you will find out what is your VCE. You can find out directly from the graph if you have the load line already drawn. Otherwise also you can find out using the equations. You can solve the equations anytime, but if you are given the load line, you can directly find it out from the graph. Okay, so that is the thing. Now one point we should mention here, how the common emitter configuration operates in the active region. Let us try to see the active region. How does the common emitter configuration operates in the active region? We first set up a IB, correct? This IB gives rise to an IC by the amplification beta. This IC, from this IC we can get a VCE. This is the order. Now as you change the IB, this is the input change happening. So in the input side, if there is some change, so if IB is varying in nature, what happens? The variation in IC is appreciable or not appreciable? Is the variation in IC, the output side, appreciable when input side is varying? What is the answer? No answer from your side? See, let us take a case. IB is 1 microampere, beta is 100. What is IC? IC is, this is 10, suppose this is
100 microampere.
10, so 1 milliampere. Now you change this to 11 microampere, 1.1 milliampere. Okay, so if there is some degree of change, so suppose till 15 or 20, suppose 15, so here you calculate the percentage change in this side and the percentage change in this side, quite much. So there is a large difference in the output side if you change the level of the input. This is also very evident from this graph that you are seeing. So if you change this value a bit, since this load line is so much slanted, this load line is slanted, obviously it will be slanted. So the change in IC is quite a lot, and the change in VCE will also be quite appreciable. This gives to a phenomenon which we call the moving Q point. So you know Q point, the name Q point was given because it is an unmoving point, but in this case the Q point moves, but it moves only due to input changes. Obviously when we discussed Q point, we also discussed this. When input changes, when there are situations in the circuit changes, Q point also will change. That is true. But here the change in the Q point is quite large, and this does not allow us to utilize the common emitter configuration in the active region very reliably. This much you can understand. These are conceptual things. There is no mathematics behind this. So we cannot use the common emitter configuration reliably when we are trying to operate the transistor in the active region. Trying to operate the transistor in the active region, what does this mean? This means that we are trying to set up the transistor as an current amplifier. The operation in active region is current amplification. That is what we are trying to use. Input side they will give a very small current, in the output side we will get a large current. This is what we are getting. This is the use of the transistor in the active region, amplification. So the amplification work is not very reliable with common emitter configuration. This you note down in your notebooks. The common emitter configuration does not produce a reliable amplifier circuit. What is produced very reliably? The operation of having the transistor either in saturation, this is a very strong point, saturation, and in the cutoff. So these two, if we are able to set up the biasing, output biasing in such a way that it is either in the saturation or in the cutoff, then these 2 points are very widely apart from each other, very much distinguishable from each other. So if by any way we are able to set up the biasing, suppose this bias voltage we are having a handle on it, so either we have it very high or have it very low, and in these two situations we are having it in saturation region or in the cutoff region. This is a reliable operation in the common emitter configuration, and this operation is nothing but a switching operation. Why I am calling this as a switching operation? You can understand that when we are in saturation, the current in the circuit, output circuit, there is some current. When we are in the cutoff operation, output side there is no current. So when there is a load current, we can think that it is the switch is on, and when there is no load current, the switch is off. So by the biasing we can decide whether the load current is there or not. So whether the transistor as a switch is open or closed, that we can decide using the bias signal. So we have a control on switching on or off the entire circuit using a transistor. So the transistor here acts as a switch, and this switch is governed by electrical signals which we can give to the bias side, give to this bias. So this is a electronic switch. This acts as an electronic switch. Okay, like the diode also was acting as an electronic switch when we are forward biasing or reverse biasing. Here also the transistor acts as a electronic switch. So there are two modes of operation that we can extract out of a transistor. One is the switch operation, another is the amplifier. One is it is acting like a switch, another it is acting like an amplifier. Because as we understood, there are 4 regions only available. We are not working in the breakdown region, so these 3 regions are available, and here in the active region it is amplification, in the saturation and cutoff it is the switching operation. So amplification and switching are the two operations which are available with a transistor. Now suppose you are given a circuit. How to know which operation it is performing? I ask you the question, this circuit I will give you, and I will ask you, tell me whether the transistor is acting as an amplifier or it is acting as a switch. Okay, so this you have to ascertain. So whether it is in the active region or in the saturation region or in the cutoff region, these three regions are possible. So you have to ascertain which region it is working in. For that case, what to do? For that case, we have to take help of whatever we have understood so far. So let us first try to see whether it is in saturation region. So saturation and cutoff are like this. This is the way of analysis. Now if it is working in the saturation region, we assume it beforehand that it is working in the saturation region. In that case, the voltage across this will be 0. The voltage across this will be 0. So what is the current in this circuit? That IC. So we are trying to ascertain whether saturation or not. The IC will be 20 by 10 kilo ohm, 2 milliamperes, right? So this can happen if this VC is 0. So we have to now see whether what is the IB here. This is important now. We cannot simply just look at IC and say anything. We also have to see what is the IB. Now you please remember, this IB is only dependent on the input side, the base biasing. This is 10 minus 0.7 by 100. Let us ignore this 0.7 for the time being, because we just want to do a very simple calculation. So IB is 10 by 100 kilo ohm milliamps. So this means 0.1 milliamp. If it is working in the active region, then IC will be beta times this IB. If this circuit is working in the active region, then IC will be beta times this IB. Beta times this IB is, beta is 50. 50 means 5 milliampere. Now you compare this IC which you have calculated assuming the short and the IC that you have calculated with the current gain. So the saturation, if this shorted current is less than the active current, that means it is working in saturation, because the saturation current is actually lower than the active current, because it rises up, right? There is a saturation region, then there is the active region. So before reaching the active region, there it is in the saturation region. And if we see the analysis here, so this IC is lower than this active region current. If this IC we found out to be greater than this current, then it was not working in saturation region, it would work in active region only, and there would be a drop here, appreciable drop because of this current. So this is how to understand whether it is working in saturation or in active region. Okay, this is the thing. So this analysis is also given in the book. One more analysis is there. with the VCE, it is not, I don't recollect that analysis. One can also utilize the one can try to understand what is the voltage across VCE and get it. Yes. So I think, yeah. So calculate the voltage VCE, assuming it is in the active region. So active region current in the output circuit is 5 milliampere. So what would be VCE? VCE would be 20 minus 10 into 5. What it is giving you? Minus 30. Can the voltage in VCE be minus 30? Because VCE we know has a direction like this. So the value must be positive, but here the value is coming out to be negative. This is also an indicator that it is not working in the active region. It is working in the saturation region. So it violates the voltage range that is available for the active region. So do you get this? Do you understand this? How to ascertain whether it is in saturation or in the active region? One way is to figure out the short circuit current, which is a saturation current, and see whether this current is less than the active region current. If it is less than the active region current, then it is in saturation. Another way also is this, that you determine the active region current IC and you find out VCE. If VCE is less than 0, negative, then it is not working in active region, it is working in saturation. This is the two way to understand whether a given circuit is in active region or saturation region. So a lot of ideas we are discussing today. Let us have a brief recap. We first discussed the output characteristics, then we try to understand what would be the saturation and cutoff Q points by doing this mental short and mental open. This idea I hope you understood, and we also understood that the Q point is quite volatile in nature and hence it is not useful or reliable to be used as an amplifier. So we use the common emitter configuration as switches, and this is the most used. The switches are those which are in any computing device. So in the computers or any our laptops, computers, as well as any small computing device, it is only switches which are working at the very ground level, at the very hardware level. It is only switches which are on or off, and these switches are nothing but transistors. They are transistors. They can be bipolar junction transistor, they can be some other transistors also. Nowadays we have quite modern versions and which are more efficient and reliable. So those transistors we use. I guess we use I think CMOS transistors in computers, where you can check in the internet also what type of transistors we use in a computer. You can get that. So but the operation of the transistors are like this. Transistors can operate either as an amplifier or as a switch. And we also understood how to understand whether a circuit is in saturation or in active region. How to ascertain that? What is the region of operation? Moving ahead, we just discuss one or two points in the remaining in the common emitter configuration. One point is this, that with temperature the current gain is varying in nature. You see, this is HFE, which is nothing but the beta parameter. This is given in the data sheet as HFE, So you can see that with temperature, this is the temperatures. With different temperature, as your IC is increasing, sorry, this is like this, as your IC is increasing, your beta is also changing. So for smaller region it is increasing, smaller IC it is increasing, but as IC increases a lot, then the beta suddenly falls. Okay, the beta suddenly falls. So this is something nature of the transistor. This is provided by the manufacturer. This one needs to keep in mind. And also you can see that in the rising region, let us only talk about this region where where beta is increasing with different with the different temperatures. As the temperature increases, the beta is increasing. Suppose we have a particular IC current 1 milliampere, then you can see that at -55 you have your beta as 50, in 25 degree you have it as somewhere in 90, I suppose, so something like that, and 125 degree centigrade it is around 150, less than 150 but very near to that. So this is the case. Now we have a concept. So I already discussed you transistor switch. So how the transistor switch operates, we set up the biasing in such a way that it either operates in the saturation region or in the cutoff region. So what is hard saturation? What is hard saturation? Hard saturation means we prevent the common emitter configuration from working in the active region. We prevent the common emitter configuration to, by chance it may come to the active region, we prevent that also. We are making it hard saturation. We will always work in the saturation region or the cutoff region. So there is no intermediate region of operation that we are allowing. How can we set that? We can set that by making the transistor constructionally from the manufacturer's end. We make the transistor such that the gain beta is very less. When the gain is very less, then it will work in the saturation region, because in the saturation region you can see that the current is quite smaller than in the active region. So if the gain is only very small, so we are actually working in the saturation region only, not going towards the active region where the current is higher. So in that manner we set up the hard saturation. Mostly you will see that beta here is in the range of 10, something like that, around 10 times the IV. So with these concepts, we finish up the common emitter configuration. There was a lot we discussed in common emitter configuration. Next day, Friday, we will move to the common base configuration. So you go through this common emitter configuration and whatever we discussed during the last 2 classes. Transistor is very important. Understanding BJT is very important, because we will also learn some more transistors in this course, and we will learn various transistor circuits. We will learn about equivalent circuit of transistor. Many different things are there, but the very basic thing that you should, the fundamental thing that you should clear from your end is how the transistor behaves. So how the 2 different junctions give rise to the phenomenon, why B junction needs to be forward biased, CB junctions need to be reverse biased, how we can set up this forward bias and reverse bias of the B and CB junction, how the VCC is contributing to the biasing, how the base side and the collector side is, the base side is quite independent of the collector side in the common emitter case, and the base side is giving rise to the current IC in the active region by multiplying it with beta times, solving the circuit. So this sort of things you should be very familiar with now. How to understand whether it is in saturation or active, how to get the saturation and cutoff Q points. So these are the various points, and this curve is very important. The output characteristic of the collector curve is a very important curve. So that's all for today. If you have any immediate questions, immediate queries, you can ask me. We have some time now, around 5 minutes. I would also like to get some feedback from your side about how the course is moving ahead, whether the pace is okay, whether the explanations are understandable. So some modifications I need to do from my side to make things easier for you. So you can discuss all these things in your class group, and your CR can communicate with me. So how, whether I need to do any sort of modification in anything, so in the pace or in the delivery, whatever. So so that can be discussed. So the CR can talk to me directly instead of all of you like writing to me personally. So you can discuss it with your CR, and whatever inputs are there, the CR can directly tell me. Okay, so since no one is having any query, it seems, so we can close the session now. So thank you for being here, and so I am closing the recording now. Thank you.